We did all that. Anybody knows where we stopped? Let me see. Let me do this, and we can. I know we finished all that. And we started decompression steel. And we did all that. And let me see. So anybody knows where we stopped? I don't think we got this far.
I think it was 5.6, the last one we did.
Okay, thank you for that. So 5.6. And that makes sense. Okay. All right. And then now design of T-beams for negative moments. I think we covered that too. But no, we did cover the compression steel.
We stopped at the slide where you went over the AS and prime, AS prime. So the next slide, yeah, we stopped right to another one.
Was it this sheet or no? Huh?
That one. Go back.
Okay. This one?
Yeah.
All right. All right. So we'll go from here then. I did just a couple of comments, if you don't mind. So today, what we're gonna do, finish this chapter. It shouldn't take us the whole 2 hours, and then I'm gonna start chapter. Like I said, I'm gonna skip to chapter 9 and explain to you the column design, so we can start in the lab working on the column design for the project. And we mentioned next week we're gonna have the midterm. Midterm is going to be from chapter 1 through chapter 5. Columns will not be included, just chapter 1 through chapter 5. And we will talk more about it toward the end of the class. And let's see, I did post a few things on Beachboard, so make sure you keep up with Beachboard. I posted some column design stuff, and one of them is an Excel sheet. I will go over that in the lab, not here. And then I posted a scholarship from the Masonry Institute. So if anybody's interested, you can contact them on that. Okay. Any questions? Any comments? All right. And I guess it looks like the summer session is going to be on campus, from what I'm seeing on the schedule. So I'm not sure what's going on with that. All right. So let's go ahead with the compression steel. We said that sometimes we have to put steel at the top, because remember we put steel at the bottom for tension, but sometimes I also need help in the compression area, so we put steel on top. Everything we put on top, we call it prime, AS prime. The bottom one is AS. And I said that we can break this beam into, look at the equal sign. I can break it into this beam. I know we covered this, but I'll quickly go over it. Where it is moment equal ASFY D minus A over 2. The only thing that AS is going to be AS1, okay, which is a portion of AS, plus this one, which is AS2. So AS1 plus AS2 equal AS. So I split AS into 2 portions, and you'll see why. Because remember, this top of the beam is going to be in compression. There will be a compression force here. That compression force has to be in equilibrium with a tensile force. Now that tensile force is going to only need a portion of the steel. So whatever that portion is, we're going to call it AS1. Then this section will be in equilibrium. The remainder of that will be AS2. okay, will be in equilibrium with the A prime S. Okay, and then we said Mn equal Mn1 plus Mn2. Mn1 will be this, and then Mn2 will be that. All right, straightforward. We went through that and we applied it, I believe. Okay. All right. So, okay, compression steel strain must be calculated to determine if it yields. We need to know what is the strain in the compression steel to see if it yielded or not. How do we know it yielded? If the strain in it is greater than or equal to F sub Y. To evaluate strain, neutral axis must be located. We need to know what the neutral axis is. Location of neutral axis depend on whether the compression steel has yielded. But like I mentioned before, we always start by assuming the compression steel is going to yield. Write an equilibrium equation assuming steel has yielded. Okay? So locate the neutral axis and compute strain steel. You'll see how we illustrate that. It's easier by numbers. If steel has yielded, continue using the neutral axis location. If steel has not yielded, rewrite equilibrium equation, relocate the neutral axis. So it's a trial and error, but most of the time, I said last time, we want to work when the steel in the top yields. Okay? So there you go. How do we do that? The ASFY is equal to that. So where is this coming from? This is coming from the force in the steel is equal to the force in the concrete plus the force in the top steel. Because really what that means is here. Let me go back to this. So if this is my section, I'm going to have a tensile force in AS. I'm going to have a compression force in A prime S and a compression force in the concrete. So the compression force in the concrete plus the compression force in the steel has to equal to the tensile force in the steel. That's really it. We covered that last time. But so this is the equation. The tensile force in the bottom steel equal the compression force in the concrete above the neutral axis plus the tensile force, the compression force in the top steel. That's why I call it A prime S. And notice that I used Fy instead of Fs. Why? Because I'm assuming the steel yields. Okay? Now C, from here, you can calculate C is equal to that, right, from this equation. And then again, from the similar triangle, we can do this here. Okay? And let me see if we have that. I think we'll show it in a second. Now, if epsilon prime S greater than epsilon Y, then the steel has yielded. And what is epsilon Y? Fy over ES. So that's how we prove it has yielded. Okay. Now, if the steel has not yielded, steel compression has not yielded, I'm just going to cover it quickly. But we're not going to have this case. Notice that when ASFY, this is the area of concrete in compression, and because I cannot replace F prime S with Fy, then I have to calculate F prime S and look at this. This is the equation of it. All right. So this is that one. And where is this coming from? This is coming from here. This is the epsilon prime S. Okay, epsilon prime S times E. So epsilon times E is what? Is a stress. So epsilon prime S times E is the F prime S. So look at that. This is if the steel hasn't yielded. Because if it yields, I can just replace it with Fy. The equation C is so now when you do this, then this is an equation going to be a quadratic. That means to the power of 2. And then you have to solve for C. All right. So this is what I just mentioned a minute ago. So there's the area of steel in tension. There's the area in steel in compression. So if I draw the strain diagram, as usual, that's what's going to be the strain. The concrete is going to crush at 0.003. The strain in the steel is going to be epsilon T for tension. And then the strain in the top steel is going to be epsilon S prime. There's D prime, there's D. So there you go. There's the tensile force in the steel in tension. And there's the compression force in the steel in compression at the top. And there's the compression force in the concrete. See that? That's what I've been saying. So let's do an example and you'll see how we do that. So determine the flexural design strength of the beam. What is the beam? This is the beam. So I have a beam like this. How much, what is the question? Yeah, what is the moment capacity of this beam? I have 4 number 11s, 2 number 9s. And the rest we know. This is D prime, this is D, of course, from here to there, and then this is 3, and this is in all this. So first one, we're going to assume steel is yielding. Like I said, most of the time, even in the exam, this is what you should expect. The steel is going to yield. All right? Because I don't want you to go through the big equation right here. Okay? Because you're going to get a quadratic equation and it's going to cost you a lot of time. So it's okay. And then in real life, this is most of the time what it is. The steel yields in real life. So again, F prime C 3000 and Fy is 60,000. So assume the compression steel is yielding and the equilibrium equation is that. Where did I get this equation from? From here. When I assume the steel is yielding, this is the equation. So you just use that equation. So let's apply that. AS Fy 0.85 F prime C B times beta 1C A prime S Fy equal 6.25. That's AS. Where does that from? Right here. AS is 6.25. This is 2. 6.25. Fy is 60 equal 0.85. F prime C is 3. B is 14. B is the width of the beam. See that? 0.85 beta 1. Why? Because we said beta 1 is 0.85 for F prime C less than or equal to 4,000. And my F prime C is 3,000. And then C, I don't know C. Right? What is C? C is this guy, is the neutral axis location. From the neutral axis to the top, that's C. I don't know that. So that remains unknown. Plus, A prime S is 2. That's the A prime S. Remember, everything primes at the top. That's 2. Fy is 60. Look at this. One equation with one unknown, C equal that. You solve for C, C equal 8.4. If you go to this other one, you're going to have a C square. So you're going to take the square root of that. And that's what I'm saying. We're not going to go there. So you find C. Once you find C, A equal beta 1C. So you find A. What is A? A is right there. Is the depth of the compression block. Remember, we talked a lot about that. So there's A equals 7.14. Now, compute the strain in the compression steel to determine if it's yielded. So what is the strain in the compression steel? Epsilon prime in compression. What is that equation? Right there. Epsilon prime C, that's the strain in the compression steel. If this value is greater than or equal epsilon Y, then my steel has yielded, then my assumption is right. Right? Because remember, I assume steel yielding, that's why I was able to use Fy. If I don't assume that, I have to put this F sub S. Strain F prime S is stress in the steel at the top. And in order to calculate that, you have to go to this big equation here. So we're going to assume it yielded, but now I have to check that. Did it yield? I find the strain in that steel, C minus D prime over C times that. C is 8.4. I just calculated that right there. Okay. D prime is 2.5. What is D prime? Right there. D prime is 2.2.5. And then C is 8.4. 0.003 is constant. It gives me that. So this is the strain. What is the epsilon Y? Is Fy over ES. Fy is 60 divided by 29. We saw it many times, 0.0207. So if the strain in the steel gets to 0.00207, it's going to yield. The strain is 0.0211, more than the yield strain. So my steel has yielded. So compression steel has yielded as assumed. Therefore, I can use this equation. See, I just verified that this equation can be used. And that's it from here on. So now determine the strain in the tensile steel. See, just go A, B, C. What is the strain in the tensile? Just apply the equations. Okay? So AS2 equal A prime S, F prime S divided by Fy. Okay? Why is that? Let me show you. Let me show you where this came from. This came from here. This came from here. See, when I broke it into two, I'm saying the force in this AS2 is going to be AS2 Fy is going to equal to, what is the force in here? A prime S, F prime S. But A prime S times Fy, because the steel has yielded. That's where this is coming from. So there you go. So here, AS2 times Fy equal A prime S times F prime S. But F prime S equal Fy. That's why I substitute that by Fy, 60. And A prime S is 2 and Fy this. So AS2 is going to equal to that. All right? Now, so let me go back to this here. Sorry. So again, I'm trying to make this section is in equilibrium. So the tensile force here equal the compression force there. Somebody could ask me a question, say, well, what happened to the concrete here? Why didn't we include the compression strength of the concrete with the compression strength of the steel? Can anybody tell me that? Why didn't I include the concrete here? Come on, anybody? Okay, the answer is because I already included it here. I included the concrete here, so I cannot include it again there. Okay, so concrete here plus 0 concrete is going to give me the concrete here. This AS1 plus AS2 is going to give me this AS. And A prime S plus 0 A prime S is going to give me that. See that? So the short answer is no concrete here because I already took care of it right there. So that's what that is. AS2, I just calculated that. What about AS1? AS equal AS1 plus AS2. So AS1 equal nothing but AS minus AS2. AS is given 6.2 and AS2 just calculated. So 4.25 AS1. So what does that mean? That means the area of steel AS1 I need to counteract the compression force here is equal to that I just calculated. See the beauty of it? You know the theory behind that. But it becomes clear when you apply the numbers. So that's AS1. And then what is epsilon T? The strain in the steel at the bottom. We know this equation, D minus C over that. D is 24. Let's make sure. D is 24. Y is 21.5 plus 2.5. That's 24. Okay. C is minus C is 8.43. It gives me 0.00557. See? So the strain in the bottom steel is more than 0.005. So I can use, so it yielded, and it's more than 0.005. I can use phi equal 0.9. See that? I just verified the bottom steel has yielded and more than 0.005 the strain, so phi equal 0.9. And I just proved that the top steel also yielded, but that one, it doesn't need to be more than 0.005 as long as it's more than 0.00207, right? And as long as it's more than this value, the steel has yielded. All right, so then look at this. Now we can calculate the flexural strength. What is the D minus A over 2 is that? D minus D prime is this. And then where do I go? Phi Mn is equal to this. Where did this come from? Let's go back to the equation. Right there. Phi Mn is equal to this equation. Mn1 is this, plus Mn2 is that. Right? So this plus that, that's what the Mn is. We multiply by phi. All right, so here you go. Phi Mn equal phi times AS1 Fy d minus A over 2. Okay, that's the first one. AS1 Fy, let me go back to that. AS1 Fy d minus A1. AS1 Fy d minus A over 2. Okay. Plus A prime S, F prime S, D minus D prime. But what is F prime S? Anybody? What is F prime S? Come on, what is F prime S value? This is the strain. Huh?
The strain of the steel?
Yeah, the strain in the top steel, right? Right?
Yeah.
Yeah, but what is that value?
Is it 2 inches?
No, the strain in the top steel. What did we say? We said that the steel is gonna yield. So what is the strain gonna be? So F prime S gonna equal what?
60 KSI.
Huh?
60 KSI.
Yeah, 60 or Fy, exactly. It's gonna be Fy. That's why we replace that with 60 here, because it's equal to Fy. You know, I would draw this equation one more time and replace this with Fy to show you that the steel has yielded, and we proved that. We just showed that. All right? So if you substitute in the numbers, then you're going to get 584.2 kips foot. See that? So this is the how much moment can this beam carries when we have top rebars. And I mentioned before, if I have 4 number 11 bars here, let's say my moment capacity is 300 kips foot. If I put another 4 number 11, my moment capacity will not be doubled, will not be 600. It will go up, but not by much, maybe 10 to 15%. Okay? It's not gonna go up by much. But sometimes we use this because our beam is not deep enough. We need more help. The concrete in compression by itself cannot resist the compression force. We give it some steel to help with that, but it doesn't help a lot. All right, so that's that. So very important example, please. We'll assign a homework to that tonight before we leave. Okay, any question on that? So make sure you know that, please. I think the next one, the steel is not gonna yield. If it's not, I'm not gonna do that. Let me see. See that? So skip 5.8. When you do this, the steel has not yielded. So has not yielded. So therefore, our assumption is incorrect. And you have to calculate, look at that, the C value. And then it's the same. It's just one more step. And I don't want to confuse you with that. So skip 5.8.
I have a quick question, Professor.
Yes.
In that instance, would you have to calculate F sub S?
Yes, F prime S.
F prime S, I'm sorry, yes.
Yes, you have to calculate that. And the way you calculate that, and I can show you that very quickly. Let me go back to the one we started here, right there. So in the way to do that is remember Fs equal epsilon S times E, right? So Fs equal epsilon S times E from strength of material. F sub S equal epsilon S times E, right? From strength of material. So this is A prime S, and then this whole thing is F prime S. right? So A prime S times F prime S, it gives me the force in the compression steel. But since my steel didn't yield, then I have to calculate that. So what is epsilon S? Epsilon S in this case is going to be epsilon prime S, right? Because it's the compression steel. So it's this value right there. How did I get that? Let me turn this off. Right there. This is the epsilon prime S. Okay, from the similar triangle, I get C minus D prime over C times Z. So I take this value and I put it right there. See that? So this is the epsilon prime S times ES. It gives me F prime S. So then you calculate it like that. All right? Does that answer your question?
Yeah, that makes sense. And
Okay.
so we used the 60 KSI because that was the
yield. Yeah, instead of doing all that, I said that the steel has yielded. So if the steel has yielded, then I don't have to worry about any of that because my F prime S is what? Fy.
right.
See, that's what makes it simpler. So
Gotcha.
that's why replace all this by Fy. So that's why I'm saying we're gonna focus on that one because in real life, that's what really happens. Very, very seldom in this case will be happen if you're restricted to dimensions of the beams and all that. All right, any questions? All right, so we did that and we said 5.8 is not gonna yield, so skip that. You can read it, it's very easy, just like I explained that. But I'm not gonna ask you that in the exam. Now 5.9, it says design the beam. So let's go over that quickly and then it just formulas. Let me erase this. So far we analyzed doubly reinforced beam, right? We analyzed, that means we determined the moment capacity. But what happened if we're gonna design one? Design a rectangular for dead load moment and live load moment. The maximum beam dimensions are shown in the figure. Use a concrete deck. So it's giving me the dimensions. A beam is 15 times by 31, and this is 3, and this is 25. So D is 28. D prime is 3. He's asking me how much steel I need at the top, A prime S. How much steel I need at the bottom, AS. All right. So how do we do that? So again, go through the steps. Compute required flexural strength, assume phi equal 0.9. Okay? Compute required flexural strength. How much flexural strength do we require? Why? Because he gave me the dead load and live load moments, so I need to calculate the M sub U. 1.2 M dead load, 1.6 M live load. There's the moments. Okay? So I need an ultimate moment capacity of 1030. So can I get Mn from that? Yeah, Mu over 0.9, right? Because Mn equal Mu over phi. So is 1144. Step B, always follow the steps, Try the maximum permissible tensile steel in combination with no compression steel. So what he's saying here is that if you're gonna put steel top and bottom, maximize the bottom steel. Maximize this. And whatever is left, then you put it on top. Makes sense, right? Makes sense. Maximize how much you put here, the rest you will put at the top. So if we want to maximize that, what do you think I'm going to do? I'm going to use rho max. So here, try maximum permissible tensile steel in combination with no compression steel. So hopefully I don't need a compression steel if I maximize that. So from table A7, rho max is 0.0181. Remember, we said you're not going to find rho max in the table, but you're going to find rho corresponding to 0.005 tensile strain. That's going to be that number. Now, AS1, right? AS1, which is the portion of the steel that we're going to do when, remember when we broke it, is rho BD. So rho is 0.0018, the maximum, B is 15, D is 28, it gives me that. Okay, so from text table A13, rho equals 0. If with this rho, I can read mu over phi BD squared. Remember that? We can go either way. This is why this is so important and so easy to use. So mu over phi BD squared from that table gives me 912. And please go, when you study, verify that number. Okay, so from here, mu1 is equal, so what happened? You cross multiply here, mu is equal 912 phi BD squared. Phi is 0.9, 912, B is 15, D is that, it gives me 804. Remember, this is mu1. What does that mean? This is mu1. When, remember that? Let's go back. Right there, when I broke it up. This is AS1, this is MN1 or MU1, right? So I'm maximizing this with respect to the concrete here. So I'm gonna put rho max for this with respect to this, but then I will know how much more I need of that. That's the idea. Okay, so that will give me an 804. MU1. MN1 is 804 over 0.9 is equal to that. So look, I have MN1 for the first portion. And I know my MN. I know how much the total moment I need. So what do you think MN2 is going to be? The difference. MN2 is going to be MN minus MN1. So this is MN2. This is how much capacity I need. How much capacity I need from this guy. Okay, from the second portion. That's MN2. See that? It's going to start making sense. Trust me, when you start doing the problem. So that is MN2. So MN2 is 250.6. All right? And then C, determine if the compression steel has yielded. Okay, there's the area. A equal that. So 7.6 is the AS1. Okay, is the AS1 7.6 times this, and we know all these numbers is that. C is equal to this. There's the stress in the compression steel. Again, 0.00214 greater than 207, compression steel has yielded. Compression steel has yielded, then I can use F prime S equal Fy. That's what I said. Most of the time, that's going to be the case. So I don't want you to bother with the other one. D, compute the area of the compression steel. There's the formula. Mn equal As Fy D minus D prime. So you substitute everything here. But A prime F prime S equal As2 Fy. Where did that come from? Sorry, we have to go back again. That comes from here. As2 Fy equal A prime S F prime S. So this section is in equilibrium. Sorry, going back and forth, but that's the only way to understand it. Trust me. All right, where is that? Where were we? We're doing 5-9, right? Yeah. So this is that. We got this. We got that. Okay, right there. So that's where that came from. So from here, I can solve As2 equal A prime S F prime S divided by Fy. But guess what? F prime S is Fy. So they look at that. They cancel 60 and 60. That's why I don't like, I wish he did another one and replaced it with Fy is equal to 2. So AS equal AS1 plus AS2 is equal to that. Try number 10 bars for AS. Okay, so at the bottom, 8 number 10 bars for here. So we need 8 number 10 bars. All right. And then the area of steel used is larger than the amount required. Compute compressive and tensile strain. So ASFY is equal to this. Remember that equation? So we substitute everything. A equal to 9.5. We check this, epsilon Y. Compression steel has Z. We are checking if the compression steel has yielded, and it has. 0.207. This is 0.022. So our compression steel has yielded. And what is the strain in the steel at the bottom? This one here, again, less than 0.0045. See that? Because we used the maximum steel, look what happened to the strain. It came less than 0.005, but it is more than 0.004. It's allowed to be used, but my phi is not 0.9. Therefore, beam is in the transition zone. And what is phi? This is the equation. Remember that? So you look at that, 0.856 instead of 0.9. But then you compute the flexure strength, the usual, is the equation, and then is that. So when you do that, look what happened. This beam I just figured is going to carry a 1021 Gibbs foot, but my moment is 1030. My moment is 1030. Where did I get that? Right there. My moment is 1030. So this beam cannot carry my moment. So it's no good. All right? So it's no good. All right? So then what we have to do, try a larger area of steel for the compression. So I'm not going to ask you that in the exam because as you can see, trial and error. So most likely I will give you the beam with the steel and ask you what is the moment capacity of it, just like the previous example. All right? So I'm telling you what the problem is going to look like. It's going to be like the 5.7 example. So here we can change A prime S and then go through the same process. Same process here. Again, phi is between that. So look at this. When you do this, then my moment capacity is 1066 greater than 1030. I'm okay. See that? The design is a back and forth process. All right. So again, 5.9. But then 5.8 we skipped. 5.7 is the one you wanna definitely make sure you know how to do. Okay, this is the one. I will give you a beam and I ask you find the moment capacity. Okay. So let's see. 5.9, 5.10. Let me see. This one, I think see if the steel is gonna yield or not. This is very similar to that. Give me dead load, live load, and B. So P is 9. Let me see if there's anything different here. This, that. Same. See, okay. So steel has not. See, in this example, look at this. Compression steel has not yielded. So skip 510. Because then you have to calculate for the person who asked earlier. See that? We calculate F prime S equal epsilon prime S times ES. So that's the same. And then you go through, it's the same thing. So skip 510. And that's it for this chapter. Any question on that? Any question? All right, let me assign you a homework problem. So you can practice that before the exam. And then we can start the column. See, this is chapter 5. Okay, calculate the design. Let's do 516 and then compute the design moment strength. And 527. So 516 and 527. Okay? And then you'll submit him. We'll submit him after the exam, so you don't have to rush on that. So this would be homework number what? 4? Right? Anybody? I think it's number 4. I'll check that though.
Yes.
So 516 and 527.
Our exam would be next Thursday, right?
Yes, the exam is next Thursday. I'll send an email to remind everybody. All right, we'll talk about it a little bit before we quit tonight. So, all right, any questions? All right, so that's it for chapter 5. I want to now go to the column. Let me open the chapter. Again, I'm skipping chapters, but we're coming back to that. 6, 7, and 8. We're going to go back to that, but it doesn't matter. I can get them out of order so we can continue our project. All right. Okay, can you see my chapter 9? Anybody? Hello?
Yes.
Okay, thank you. So we're gonna go to chapter 9. Last time I gave you a brief thing about how you choose the size of the column, and we're gonna go over it again here. You'll see it's a very nice, very easy chapter, so we can keep going. All right. So types of compression members. Compression member is a column, really. It's subjected to compression. We've seen that in deformable body, strength of material, and we studied the buckling of columns and all that stuff. So types of compression members. We have short compression blocks, pedestals we call them. You know, the older homes that were built in the 50s and 60s, early 60s, they were built on something called raised foundations. So, you know, if you live in one or you've seen them, it's a raised foundation. The house is off the ground by about 18 inches. So there is a crawl space underneath. And the reason they did that, they wanted to run the utilities under the house. So you have the water lines, the sewer lines, and all that stuff. Nowadays, they don't do that anymore. Okay, it's all with slab on grade. So that when it is raised foundation, the houses were set on something called pedestals. It's nothing but a piece of concrete about 18 inches high, and it supports the girders under the house. Okay, even Home Depot has some of those nowadays. So in theory, that's a column. That's a compression member, but we call it a pedestal because it's short. Short reinforced column. This is the one we're going to focus on. Short meaning they are the typical heights, 8 feet high, 9 feet, 10 feet, maybe 12 feet high. Those are considered short. Versus long. What's the long column or slender? Those are the columns you see at LAX, Long Beach Airport, Convention Center, when the columns are 35, 40 feet high. Those are long columns. Why we care about that? Because the short column, most of the time, the failure is going to be in compression. It's going to crush. But the long column, when you have a column 40 feet high, another mode of failure can be, beside the compression, is the buckling. That's what we studied in the deformable bodies. Remember, we looked at KL over R. That's to address the buckling aspect of the column. Because if the column buckles too much, even if it doesn't crush, that's a failure. You're not going to see a column that buckles to 24 inches to its side in the middle and stay in that building. Okay, so that's what that is. So our scope is the short reinforced column. That's what the one is. Short compression block, as I mentioned, height less than 3 times least lateral dimension is again very 24 inches. May be designed as unreinforced or plain concrete. Those, they don't have even reinforcement. They don't need reinforcement. They're just plain concrete. Maximum force is this, 0.85 phi F prime CAG. Okay? Again, this is coming from, again, look how powerful this equation we learned in deformable bodies. Stress equal force over area. Force equals stress times area. There you go. There's the stress in the concrete times the area. But we don't use the total stress. We take only 85% of that. And on top of that, we reduce it by phi. And look at phi is 0.65. We'll talk about that. So again, stocky members, they are stocky. You know, they're fat, stocky. That's why they material failure. If they're gonna fail, they're gonna crush. You're not gonna buckle or yield or anything like that. Maximum load unsupported is controlled by the section dimensions and strength of material. Right? The maximum load is gonna be how big that thing is and how strong the material is. There's nothing else. There's like no steel to consider, nothing. Slender reinforced column. Now remember, this is the short reinforced column. Slender meaning thin. What's going to happen to that? Bending deformation. It's going to bend. Secondary moments. It's going to have a secondary moments, as I'll show you in a second. Instability or buckling. We talked about that. All right? Let me see about secondary moment. Yeah, there's a secondary moment. What happened to the secondary moment is that if you have a P applied and then the column buckles so much at the distance delta, what do you think happened when you take P times delta? There's going to be a moment. Now we call that a secondary moment. Okay? So we should definitely take that into consideration in case of severe buckling like that. But that's not going to be our case. Okay? Because we're doing the short columns. P is the axial force, M is the primary moment. Primary moment meaning the applied moment, the primary. The one that's coming from the wind or earthquakes or something. But the secondary moment is the one coming from the buckled shape of the column. All right? Types of columns, we have tied column, spiral column, and composite column. So the best way is right here. So what's a tied column? The first one. Tied column is this. This is what we're going to focus on. Is a column. This is the height of the column. Cross section of it is this. We have minimum 4 bars, 1 in each corner, and we have ties connecting the bars. That's why we call it tied column. Okay? So this is the elevation of it. Look at this. These bars are this one. These bars are that. And we have ties. The ties is just like the stirrups we showed in the lab, but they are spaced at certain distance. We're going to design that. These dark spots, we call them the longitudinal bars because they are the long ones along the column. And then these are ties. See, in columns, we call them ties. In the beams, we call them stirrups. Okay? So that's what that is. Another type of column is spiral columns. Spiral. Why do we call it spiral? Because the steel inside, instead of ties, we have a spiral. You know what a spiral looks like. Okay? So we call that spiral column. Sorry. Now, this is a much better column than the other one. Why? Because when you have a spiral like this, and this area, this distance between this and that is very small, 2 to 3 inches. So what that's going to do is going to contain the concrete inside the column. When it shakes during earthquakes, yes, the outside concrete is going to shake off, but the inside is going to be contained. That's why it's a good column. You don't see that in columns, very seldom, I mean in buildings. But freeways, 100% of the time. 99% of the time these days, almost 100%. So watch when you drive on the freeway and they're forming a new column and look at and see. It's a 5 feet diameter with a spiral reinforcement. It's almost a standard. 5 to 6 feet diameter. Can you imagine how big that column is? And then, of course, we have the rebars inside. So inside we call it the core. Outside we call it the shell. The shell is the outside. And then this is the spiral. Okay, that's spiral column. We'll talk more about that. The third one is the composite columns. Composite column is just like it sounds, or these days we call it hybrid. So it's a combination of two materials. So I have a steel column right there. This is a top view. Then if I encase it with concrete, it becomes composite. Or if I have a structural steel pipe, I fill the inside of it and the outside with concrete, it becomes composite. We never design those for a new building. Never. You do this if you are trying to retrofit a building that's existing and you're trying to add the axial force capacity of those columns. Then you do that. But if you're designing from scratch, you don't do this. You do it either with concrete to carry that load, or you do it with steel to carry that load. But this is for retrofit applications. All right? So that's what that is. And you will see the design is very simple. The design is very simple. It's just the strength of the steel plus the strength of the concrete. And notice that when we do that, so we have a steel column, and we're going to put concrete. Look what we did. We put rebars on the outside. We put the ties around this, and then we put the concrete. Yeah, you don't want to pour the concrete without these rebars because it's going to fall off. That's not going to stick good to the steel column inside. Here you don't need rebars because you have a steel pipe, and this cover is only the cover, so you don't have room to do that. So okay, so this is how we do that. And then this is going to contain the concrete so well you don't need anything else. Okay, so now we're going to go ahead and zoom on the tied column first, then we'll go to the spiral. So tied column, ties increase column strength. So the ties increase the column strength. Ties hold longitudinal bar in place during construction. Of course, you have 4 bars up. What's going to hold them in space? You need those ties to form the cage. Ties prevent longitudinal bars from buckling after cover spools. So the ties here prevent these bars from buckling out. Okay? Now, the only thing is, long time ago, before one of the famous quakes in California, I forget the name of it. It's not the Northridge, it's the one before that. The spacing between these ties used to be about 12 inches. No longer the case. That was too far, too much. They found out in quakes, this bar bent in between. Yeah, the tie did its job, but between the ties, the bars buckled. So nowadays, this distance is gonna be much smaller, especially when you consider earthquakes. Okay, it's gonna be like 6 inches, 5 inches, and all that stuff. Okay, so buckling. Tied columns are usually, but not always, rectangular in shape. So tied columns, mostly rectangular, either a square or a rectangle in shape, but not always. Sometimes you could have a rectangular column with a spiral inside. Honestly, I've never seen that, but it could be. It could be, but most of the time it's known. If it's a round, it's a spiral. If it's a square or a rectangle, it's a tie. But the code allows that. See, tied columns are usually, but not always, rectangular in shape. And square is a special case of a rectangle. Spiral columns are usually, but not always, circular in shape. They could be rectangular, but mostly is circular. Helical spirals. Okay, so that's the spirals could be helical, the geometry of it. Spirals are more effective than ties in increasing column strength. I told you why, because they contain the concrete inside. Spirals are loaded in hoop tension. When the load is applied, the spiral itself is loaded in hoop tension. So there's a tension force in those hoops, okay? When compression load is placed in a column. Why is that? Because they're trying to contain the concrete inside. The concrete is pushing out, so it's putting that hoop tension. Hoop meaning circumferential, you know, that's what a hoop means. Spiral columns are more expensive than tight columns. Absolutely. Why? Because it's not easy to make that spiral. Okay? And then, you know, speaking of cheap labor, the labor can easily make those ties, but they cannot make the spiral. Excuse me. That's why the spiral has to be made in the shop, in the factory. Spiral columns are better for seismic applications. That's why we use them for bridges. All right. So how do we design that? How do we design the column? Look how simple it is. And you know me, I'm not going to give you an equation to just plug in numbers. This is the equation. But I'm not going to, oh, this is the equation you just used. No, let's see, what is it? Where did it come from? So what is the capacity of a column in axial load? How much load can this column carry? How am I going to find out? Remember, my column, as you can see here, is going to have concrete and is going to have steel. So remember, very early on, we said concrete is good in compression but weak in tension. So we introduced steel to help the concrete. That means steel is good in tension. At that time, I said that, okay, steel is the good in tension or strong in tension. Does it mean it's weak in compression? The answer is no. The answer is the steel is good in tension and compression. So what do you think the capacity of this column is going to be? How much load the concrete can carry plus how much load the steel can carry. And I add them together. That's it, in compression. The concrete compression load plus the compression in the steel load, I add them together. That's the capacity of the column. But of course, we apply some safety factors and all that. That's the idea. So how do we do that? There you go. P. Let's start with the steel. Again, stress equal force over area. Force equals stress times area. So how much force can that steel carry? Look at that. The stress in the steel, Fy, times the area of the steel. Very simple. Notice that we assume that the steel is going to yield in those. That's why I used Fy instead of Fs. Right? So this is how much force the rebars can carry based on their area of steel. How much the concrete column they can carry, the concrete in the column. Again, it's area times stress. What is the stress in the concrete? F prime C. But we only take 85% of that. So 0.85% F prime C. Remember, we never took F prime C. We only took 85%. That means we left 15% for safety. What about the area? It should be the area of the column, right? The area of the concrete. But I have to be careful. If I take the area of concrete here, which is this column, but I displace some of the concrete by these bars. So my gross area is this B times H, but my net area is going to be the gross minus the area of those 4 bars. Does that make sense? So I have to subtract that. Although it's very small area, but still I have to subtract that out because there is no concrete there. So that's what this is. So the gross area is the column area from the outside. I subtract the area of the 4 bars, which is the area of the steel. And that's my area. I multiply by the stress. It gives me the P. See that? How simple? But this is why it is like this. AG is the gross column area. The gross column area meaning the outside to outside, the gross. This times that. Okay? The total area of the column. And then AST is the area of the longitudinal steel. Make sense? So this is the theory behind the axial capacity of the column. But you will see now we're going to apply some other factors to it before we can start using the equation. But this is the start. Okay, failure of columns. Tight columns, how does the tight column fall? Of course, first of all, the cover, the outside, is going to spoil. Spoil meaning it's going to fall off. Makes sense, right? Because it's like 2 inches, 2.5 inches thick. If you start doing anything, it's going to crack and it's going to fall off. So cover spoils, and unless ties are closely spaced, longitudinal bars will buckle. That's how the column will fail. Spiral column, cover will spoil, right? The outside is fine, but longitudinal bars and concrete core are confined. Confined meaning held together by the spiral and remain intact. That's why this is a better column than that. And you will see the phi value we use for this different than the phi value we use for that. Okay, you will see why. And a spiral cage is designed to have a strength equal to the spooled cover. So the spiral cage is designed to have the strength of the spooled cover. We'll see the equation. So strength of the spiral. What is the shell strength? The shell strength, that means the outside. Again, let's look at this. The F prime C, right, times the area. The area is what? AG minus AC. Let me take you there. We are talking about the area of the cover right there. See, this is the outside area. So what is that equal? The gross area of the column minus the core area. The inside. What's left is the outside. That's what that is. So there you go. AG minus AC. AG is the gross column area. AC is the area of the concrete core. Spiral strength is equal to 2 rho S AS Fy. Okay, so and that's what here he told me. You can just use the equation. He said spiral cage is designed to have a strength equal to the spooled cover. Okay, the strength of the spooled cover. That is this one right there. Okay, so rho S is the percentage of the steel. And just use the equations, you'll see how we apply it to the example. So the concrete strength equal the spiral strength. And then from here you solve for rho S, meaning how much area of steel, how much the steel ratio for the spiral is going to be is that. So instead of doing this, the code say use this. So just use that one. So how much spiral we need is 0.45 times this, which it came from here. Okay. Now, spiral steel percentage. How do I calculate rho S is equal volume of spiral in one loop divided by volume of concrete for a pitch of S. S is this, and again, you'll see the example. It's very simple to apply those equations. S is this distance from here to there. We call it the pitch. Okay, so S is equal to that. All right, and then, of course, rho S equal V via spiral over core. Just use the equation. This is the rho S is equal to that. Diameter of the core inside, the bar diameter of that. Okay, and then here you go. So this is the spiral. There's the S value I told you, the pitch. And then there's the diameter, dB is the diameter of the spiral. And then DC is the diameter of the core. Notice it goes from the outside of this spiral to the outside, and then H is the diameter. And you'll see that's all we need for the examples to come back to that. All right. We're almost there. Then we start doing the examples. Almost there, guys. Now, this is very important. ACI code requirements for CIP. CIP stands for cast in place, columns. Okay, so that's what that is. That means they're not precast. That means they are formed and put on site. Every problem we do, we're gonna have to check all these, and you will see. We'll apply it in the exam. So what are we have to check the ASI. First one, it says percentage of longitudinal steel. How much longitudinal steel I can put in the column. The percentage, that means the row S, has to be between 1% and 8%. It cannot be less than 1, cannot be more than 8. And you will see in the example, it'll stick very easy. Second requirement, at least 4 longitudinal bars must be used within rectangular or circular ties. If you have ties, you need minimum 4 bars, right here. If you have ties, you need minimum of 4. You cannot put 1, 2, and 3 and leave this with no bar. It doesn't make sense. So you need 4 minimum, okay? Can I put 6? Yeah, 8, yes, but you cannot do less than 4. How about the spiral? Spiral, the code, you will see the next one is called, you need a minimum of 6. Cannot have 4 only, you need 6 minimum, all right? That's where we're going with that. Here you go. At least 4 longitudinal bars must be used within rectangular or circular ties. So if you have rectangular ties or the tie could be circular, you also need 4. But very seldom you'll have circular ties, honestly. It's always rectangular. There you go. At least 6 longitudinal bars must be used with spiral ties. See that? If you have spiral ties, then you need 6 bars. The practical minimum column dimension is about 8 to 10 inches. But I've mentioned many times in the lab, although the code allow you to do 8 to 10, but in real life, 12 inches should really be the minimum. And that's what we're doing in the lab. Okay? Look at it. I mentioned it before. It allows you to go down to 8, but 8 inches is very small column. 12 inches is fine. 12 inches is very practical, good size. So every problem, we're going to check those, and I'll show you. For tied columns with number 10 and smaller longitudinal bars, so if I have columns with number 10 bars and less, the ties has to be number 3. We're gonna talk about that a lot. If the column has number larger than number 11 bars, then the ties has to be number 4. Okay, but most of the time in real life, we are in this case here. Okay, in real life, you're number 10 or less. For tied columns, this is very important. For tied columns, how do I know how much ties I need? It says the maximum spacing of ties is the smallest of. So from here, I decide whether I need number 3 or number 4. Most of the time is number 3. So what is the spacing between them? You have to take the smaller of these 3. First one is 48 times the tie bar diameter. If I'm using number 3, the tie bar diameter is 3 over 8. So 3 over 8 times 48, that gives you 1 spacing. Then you take 16 times the longitudinal bar diameter. If my longitudinal bar is number 8, my diameter, or 7, my diameter is 7 over 8 times 16, it gives me another number. Or the least lateral column dimension. If my column is, if my column is, excuse me 1 second. Sorry about that, guys. I had to take that call. All right. So, so the least common dimension, let's say I have a column that's 12 by 16. So my least dimension is 12. So that would be one of the numbers. If my column is a 14 by 14, so it's 14 because both dimensions are the same. Okay, so that's that. And you'll see very easy to apply. And then for also the code for tied columns, ties must be arranged so that every corner and every alternate longitudinal bar has lateral support provided by a tie bent around You can read that. So the best way I can explain this is this guy here. So that's what he's saying here. What he's saying is that if you have a column with 4 bars like this, the maximum spacing here can be 6 inches maximum. Maximum for what? That means I don't need a tie here. So if maximum 6 inches, you can do this arrangement. Here also, you can do this, maximum 6 inches. It's gonna make more sense when I show you this. Next one, if this spacing is greater than 6 inches, then you have to insert this other leg here. See, greater than 6 inches, you have to insert this leg. Greater than 6 inches, you insert that leg. Or you can do this. The idea of this is that they want every bar to be supported by a tie. As you can tell, every bar is supported here, here, and here, if the spacing between the bar is greater than 6 inches. But when the spacing is less than 6 inches, then you don't need that. All right, you don't need that. But honestly, it's a good practice to do that. Whether you need it or not, it's a good practice to do that. Your column will be much better column this way than the other one. All right, so that's what this is saying right there. And then supported bar, again, you can do this. If this is again less than 6 inches, you can do every other one. If this is all less than 6, you cannot have more than one. You can do this, and then every other one you have to do that. That's also is said right there. Okay, spiral may not have diameters less than 3/8. The spiral cannot be less than number 3/8. Cannot have a pencil size to do that. The clear spacing between spirals may not be less than 1 inch or greater than 3. See that pitch distance cannot be less than 1 inch or greater than 3. So most of the time it's going to be 3 inches. Capacity reduction factors. Remember, I told you the equation for the column. This is the equation, but we have to reduce this capacity by factors of safety. So what are those? So capacity reduction factor, failure of a column is more significant than failure of a beam, right? Like I mentioned before, if a beam on the 3rd floor, remember the beam carries a tributary area, let's say it's 6 feet wide. If something happened to that beam, the tributary area around it is going to come down, but nothing else, because it's carrying that piece of the floor. Remember, we've been doing it in the project. That's a beam failure. But what do you think, what happened if a column failed on the 1st floor of a 10-story building? Everything above that column is coming down. See that? That's what it says. Failure of a column is more significant than failure of a beam. For tied, remember for the beam, how much phi we use? 0.9. So we calculate the strength and we only take 10% for safety. But look at the columns. For tied columns, phi is 0.65. Meaning that we only take 65% of its strength. 35% of it is for safety factor, because we don't want this 10-story building to come down. For spiral column, we count on 75% of that. It's better than that. That's why we raised it. We count on 75. We leave 25% for safety factor. Okay, makes perfect sense. So that's why you will see we're going to add these to the equations before we start using them in design. What else we need to do? Yes, in our project, our columns are axially loaded only. There's no moment. Why? Because the moment to those columns comes from wind or earthquakes. But we said that we're going to design it for earthquake, but I'm going to take care of those moments and all that by shear walls. So the column's still not going to feel the moments. But we have to anticipate some moment, even if there is no wind or earthquake. Why? Because what if the construction workers did something wrong and the the way they form the beam and the column, and the way the beam sitting on the column is not perfect, because it has to sit right through the centroid for it to have zero moment. If it sets off a little bit, it's gonna have a moment. Okay, because force times the eccentricity. So there you go. There's the force times eccentricity is gonna give you a moment. E is equal mu over P. Now, to account for that, we're gonna call those accidental. That means it's not, it wasn't meant to be there. It's as a result of a construction fault. To account for accidental eccentricity, the code uses a factor alpha. So look at that. So for tight column, we're gonna multiply that equation by alpha 0.8. So that equation, after we reduce it by 35%, we're gonna reduce it by 20% more. That's why alpha is 0.8. And then for the spiral column, we're gonna reduce it by 15%. See how much factor of safety we put in our design, especially in columns? Because nobody wants to take chances. So if I do that, then this is the equation becomes like that. Remember, this is the original equation. We multiply it by phi, we multiply it by alpha. And we multiply the load by phi. Pn is equal to that. So this becomes P sub u. Okay, for spiral, we said phi is 0.75, alpha is 0.85. Again, right here, alpha is 0.85. And then phi is 0.75. See that? So you just put them in. 0.85, F prime C, everything is the same as that. For tight columns, phi is 0.65, alpha is 0.8, and then everything is the same. And that's it. These are the design equations. See, if I tell you this is the equation, go ahead and use it. You don't know where every number coming from. But we explained that. We started with the equation. We started with the steel, with the concrete, with the factor of safety for moment, and factor of safety for compression failure. That's the equation. See that? That's why I told you from beginning, I will never give you something that you just blindly apply. Now you feel comfortable, confident. This is where the equation came from. All right. So that's it. That's the chapter 9. We're gonna do design example. Okay. Just give me 1 second, please. I need to grab some water. Sorry, I'm back. I had to grab some water. All right. You'll see the example, very nice, very easy. And this is the one you need for your building. 9.1, okay? Very comprehensive. Look at that. It says design a square tied column. We know it's a square when it's tied. It's not a spiral. To support an axial dead load of 130 kips and an axial live load of 180 kips. You already calculated the loads for your columns. Remember, that's why we've been doing stuff. You already know your PU dead load. You already know P dead load and P live load, and you calculate the PU from that. 1.2 P dead load, 1.6 live load. Begin using approximately 2% longitudinal steel. Remember we said a minute ago, the steel is between 1% and 8% of the area of the column. Is very normal, very practical to start with about 2% approximate. We'll say approximate, you'll see why. because as we go through the design, things gonna change a little bit, but it's not gonna be too much off. It's gonna be a little bit over, a little bit under, but as long as we're within 1 and 8 is fine. A concrete is 4,000 and 60,000. That's our project. Okay, so how do we do that? Look how easy and very nice, very powerful example. We determine P sub U, 1.2 P dead load, 1.6 P live load, equal 444. For tight columns, what did we say a minute ago? Phi is 0.65, alpha is 0.8, right? We said that. Let me show you again. Right here, alpha is 0.8 for tight column, and phi is 0.65 for tight column. Very important. So that's what that is. Then ahead and write the equation. Okay, you write the equation. Which equation? This is the equation for tight column. This is the bottom one. You write this equation right there. Very simple. That's why I wanted to get you this, get it out of the way. So this is the equation. You start plugging in numbers. Phi Pn is what? Is Pu. Phi Pn is P sub U, which we just calculated as 444. So 444. Phi is 0.65. 0.8 is the alpha for bending. 0.85. F prime C is 4. Ag, I don't know Ag. I'm looking for the size of the column, so I don't know that. So I'm gonna leave it AZG, which is the gross area of the column. Okay, minus AST. I also don't know AST, so I have two unknowns. How am I gonna do that? Now remember, rho is equal, and let me write it here. Rho is equal, just like in beam, the area of steel, AST, divided by the area gross, right? The rho is always the area of steel divided by the area of concrete. So what do you think my AST is? Rho times AG, right? AST is rho times AG, and that's, what did we say, rho? 2%. So this is rho and AG is that. Is that clear? So that's what that is. Sorry, I should have cleared that. What happened here? Can you still see my screen?
Yes.
Okay, thank you.
We're still on 9.1 though.
Yeah, yeah. Okay, are you with me now? This is the beginning of the example. Is that what you're saying?
Yeah.
Okay. So we calculated P sub U, and then this is the equation. So AG, we said we're gonna leave it AG as unknown. AST, I'm gonna put it rho AG, and I said rho is 2% because that's what I said. Begin by approximately 2% longitudinal. That's rho. So 2%, that's 0.002 equal, plus Fy is 60, FAST is again 0.02 AG. Look at this equation. You have one unknown, the AG. So solve for AG, it comes to 188.4. Since I'm saying a square, take the square root of that. Square root of that is going to give you, I don't know, a little bit closer to that, but you had to round up, so it becomes, use 14 by 14. And try to use even numbers, like I said, 12 by 12, 14 by 14, 16 by, and so forth. So if I do a 14 by 14, what is my area? 196, greater than 188, so that's fine. All right, that's what you're going to do. So now I found my size, the size of the column. Does that make sense? Now, what is area of steel? How much area of steel I need? Okay. Now I go back to the same equation. Select the longitudinal steel. So again, everything, you know this. Now I know AG. AG is what? Is not this guy, is the 196. That's what I needed, but I chose 14 by 14, so my AG is 196. So I go ahead and substitute AG is 196, and guess what I do with AST? Now my AST is the unknown. I leave AST unknown, and AST unknown, and I solve for AST. AST is equal to 3.31 inches square. I go to the table, I can pick 6 number 7 bars. That gives me AS equals 3.61. See that? Just a little bit over that. See that? That's it. That's how you design a column. So with your knowing the load, okay, it's a tight column. You can easily size your column. Start by 2%, like we said. Size your column, 14 by 14 in this case. Go back and calculate the area of steel and pick your bars. All right? So your column is 14 by 14 with 6 number 7 bars. What else left in the column? What about the ties? The ties right here, the tie design. You have to check these 3 things. 48, and remember, we chose number 7 bars. Number 7, we said any bars up to number 10, we use number 3 ties. So I'm gonna use number 3 ties. So what is the spacing between number 3? Spacing between number 3 is 48 times the tie bar diameter, 3 over 8, 18 inches. 16 times the bar diameter of the longitudinal bar. What is my longitudinal bar? Is number 7. Okay? So what is the bar? 7 over 8, 14 inches. Or least column dimension. I chose 14 by 14. So what is my least dimension? It's 14. So I'm gonna pick the least one, 18, 14, 14. So I'll pick one of those. So then number 3 ties at 14 inches on centers. See how easy? Very easy. Very easy. Now you can design your columns in your project. One more thing we have to do.
Professor,
Yes.
can you confirm again why it's 7 over 8, please?
Because remember, this is 16 times the bar diameter of the longitudinal steel. Huh?
Longitudinal, right?
Yes, those are the long bars, not the ties.
Thank you.
Then I said my longitudinal bars is number 7. So what did we say before? If you know the bar number, you divide by 8 to get the diameter. 7 over 8. Remember that? Or you can go ahead and look it up in the table. For number 7 bar, this is the diameter of it. Is that clear?
Yes.
Okay, thank you. So I'm going to use number 3 ties at 14 inches. What else I have to check? I have to check the other code requirements. One of them is minimum 4 bars, because I have a tight column. Minimum 4 bars. I have, how many I have? I have 6 bars. So I meet that. Okay? And then the other one is, what is my ratio of, before I come to this? Steel ratio. Remember I said the steel ratio has to be between 1 and 8. 1% and 8%. What is my steel ratio? I chose the area of steel is 3.61. So what is rho? AST over AG. AST 3.61 divided by 14 times 14. My rho is 0.018. Between 1% and 8%. See that? That's why he told me approximately 2. Look what my actual rho came out, 0.018. But without assuming 2%, I could not solve this. Without assuming 2%, I could not put that here. So that's why I start with 2%, and then I will find actually what is rho, which is 0.018, between 8 and 1%. And then number of bars is 6 greater than 4. And the other one is the longitudinal bar clearance. What is the clearance between the bars? You can do that, 9 over 2 minus 7 over 8. Okay, so this is like greater than the diameter. So and I think there's a sketch. The 9 is right here. So he's trying to take 9, divide by 2 to find the spacing, and then subtract the diameter of the bars to find what is the clear spacing between these bars. Remember to compare them to 6 inches, whether are they 6 inches or not. So that's what that is. And then minimum tie size is like, remember, since we're using number 7 bars, we use number 3 ties. And then this is the sketch of the column. So very important in the exam and in your project, you have to sketch the column like this, because that's what you're going to see on the blueprints of the in the construction site. So so we said 14 by 14 is my column, 6 number 7 bars. Look at this, 6 number 7 bars. This distance is 2.5, 2.5. That's always almost the case. Okay. And then if this is 2.5, then look at it. From here to there is 2.5.
Hi, babe.
Okay. And this is 2.5. So this
Okay,
is 5.
sounds
Out
good.
of 14, I have 9 left. So if 9 left divided by
The
2, this is
soup.
4.5, 4.5.
And Mia ate her.
Right? It's less
and
than
Mia ate
6
her bone,
inches. So I don't need
her chamorro.
I don't need another tie here.
Mm-hmm.
Okay, that's what we're talking about. See how
Okay.
nice? And then you do 9. It's very nicely drawn. That's what I want in the exam and in the project
No,
side.
yo vente.
And then guess what? This is done. This is a perfect design for a column. That's all you have to do.
What
And
nos
guess what?
hacemos?
From here on, all I can change is
That sounds fun.
the dead loads. I can change these numbers.
Okay.
That's it. I cannot change anything else. So you follow the same procedure. Now, in order to, and we'll do that in the lab tonight and tomorrow. In order to do this, I did a spreadsheet for you, and that's what I posted on the on Beachboard. If you plug in your P, then you will get all these numbers. Okay, and you will see how that's done. Very easy. So, but in the project, I want you to do one of the stacks. Remember, we have 4 different stacks. You do one of them by hand like this, and then the other 3 you use the spreadsheet that I wrote for you. Okay, or you can write. You should have done it by yourself, but I wrote it, and then please review. We'll go over it in the lab and see that. And that's it. So the other one, the spiral, we'll illustrate next time. See, yeah. I wanted to do the rectangular because that's what we have in the column. So what I might do in the lab is for every section, finish the spiral and then talk about your project columns and show you the spreadsheet and all that stuff. All right. Any question on that? Okay, if not, then we're done. We're done for today, and I will see some of you at 7 today. Oh, let me take attendance before we go. That's why I left some time for that. So any questions, please shoot it. See how nice it is to skip those chapters so you can keep going on your project. This way you don't run out of time, and I hope you are taking advantage of that. I am worrying about your time, so please take advantage of that. And then after this, the project is done except the seismic loads. And then we will start working on that after the exam. Okay. All right. Let's see. Faisal.
Yes, here.
Okay. Abdullah.
I'm here.
Okay. David. David Rashid.
Here. I'm here.
Okay. Asma.
Here.
Okay. All right. Ahmed.
I'm here.
Okay. Alexis.
Here.
Okay. Griffin Brown.
Here.
You. Janelle.
Here.
Thank you. Jacqueline.
Here.
Okay. George.
Here.
Thank you. Garrett.
Here.
Thank you. Joycelyn.
Here.
Thank you. Arba. Arba, Iskandari.
Here.
Okay, thank you. Andrew.
Here.
Alexander.
Here.
Okay, Benjamin.
Here.
Thank you. Binyam. Okay, missing. Jose Pablo.
Present.
Thank you. Adis.
Here.
Thank you. Andrew. Hong.
Right here.
Thank you. Gabriel.
Here.
Okay. Jean Paul.
Here.
Thank you. Raymond.
Here.
Thank you. Li Ping.
Right here.
Thank you. Christian. Sean.
Here.
Okay. Jonathan.
Here.
Thank you. Michael. Ravi.
Here, Professor.
Thank you. Christian. Montes.
Here.
Thank you. Patrick.
Here.
Thank you. All right. Craig.
Here.
Minwoo.
Here.
Thank you. Daniel Dang.
Here.
Okay. Prado.
Here.
Thank you. Myra.
Here.
Thank you. Hassan. Hassan. If anybody knows him, tell him to come to class. This guy is not coming to any classes. I'll email him. Alexander.
Here.
Thank you. Armando. Carlos.
Here.
Daniel.
Here.
Thank you. Tan.
Here.
Okay. Paulino. Vincent. Missing. Okay,
He
Gene.
just put in chat his mic isn't working. He's here.
He is? Okay.
Yeah, he put it in the chat. His mic doesn't work.
Oh, okay. Okay, thank you. I'll see it. And Gene Watson.
Here.
Thank you. All right, everyone. Thank you very much. Please keep attending, guys. This is a lot of good stuff we're covering, as you can see.
Hey,
So, question?
Yes, sir. This doesn't apply to everybody else. It just applies to myself. I just wanted to give you a heads up that I will be sitting in on the lab in a little bit because I won't be attending tomorrow.
Okay, that's fine. Just remind me tonight in the lab, huh?
Okay, yeah. Thank you.
We'll take attendance there too.
Hey, same link, right?
Yeah, same link. Everything is the same link.
All right, Kill. Thanks.
So please, everyone, keep moving on your projects. We'll talk about it in the lab. Now you can do your columns, and you saw how easy it is, and then we can finish the building. Okay. With that, let's go have some dinner, and we'll meet again at 7. Thank you, everyone.